All right, so today we are going to be looking at exponential functions in context, sometimes. And then we are going to be modeling data with an exponential function. The other thing we're going to do is this first part where you have a table of values and it tells you that there is a proportional change. But it doesn't look like there is. And the reason it doesn't look like there is a proportional change is because a constant has been added or subtracted to it. So there was like a vertical translation that you're going to have to figure out what it is. So this is kind of like solving a puzzle. So on example 1, we're going to look at, when you look at these output values originally, it doesn't look like you're multiplying or dividing by the same thing each time. So what we're going to do is add or subtract a number, a relatively small number, until you can see that proportional growth or decay in your output. So just try this in your head. Look at these outputs, add or subtract the same number from them until you can see that you're multiplying by the same thing each time. Does anybody figure it out? -1 works. -2 I don't think works.
I said
Times. Okay, so we're going to subtract 1 from each of these output values and you get these. And then like he said, you can tell once you subtract that 1 that you're multiplying by 2 each time. All right, nice job. So now what we're going to do is write the equation for this one. All right, but we're going to start off and write the equation for this one. So f of x minus 1 is equal to, and these are going to be exponential, which means it's going to be a times b to the x. Do you guys remember what a is in general? It's the, not an x, it's the initial value. Is that what you said? Okay, sorry, it's the initial value. So it's the value of the function, this value, when x is 0. So on this first one, the initial value is 6. And then b is the base, or the common ratio, which you're multiplying by each time. So what is that for 2 to the x? Okay, so we've written an equation for this one. What we want is an equation for this one. But that's okay, that's easy to do. That is just f of x. So what we're going to do is just add 1. All right, and then we can check that real quick. I'm just going to go to the table. Oh, I didn't. Okay. I'm just going to go to the table and go to 0. And it should match the original f of x, and it does. All right. So let's look at the next one. Whoa. So what I want you guys to do, and Will's not going to figure them out for all of us. What I want you guys to do is take those outputs, and I want you to either add or subtract something relatively small until you can see that there is a proportional pattern. All right, so what did you guys add? 2, good. So what we'll do is we'll start off and we're going to write an equation for the purple column, the g of x plus 2. Initial value is 4. What are we multiplying by each time? 3. All right, and then to get the equation for g of x, we're just going to subtract that 2. All right, so I want you guys to try to do C all on your own. So after you get your table as proportion, then write your equation for the table, please. So that's a new standard for me. I mean, I taught it last year, but that's not something that is super common that you see. But I like it because it's really using your brain in a different way to figure it out. Okay, the other stuff we're going to do is I think is going to feel kind of familiar because we've done it with quadratic and cubic and other types of polynomial functions. And so to be able to write the model for an exponential function, you need one of two things. You either need the common ratio and the initial value, kind of what we knew on the tables, or you need two input-output pairs. So in example 2, we have a contextual situation where we can pull out two input-output pairs. So for 0 to 30 minutes, the number of fans inside a large sports stadium can be modeled by an exponential function, f of t, where f represents the number of fans inside the stadium t minutes after the door opens. There are 47 people in the stadium 2 minutes after the door opens. So the input is going to be 2, the output is going to be 47. And there are 2,602 fans in the stadium 20 minutes after the doors open. All right, and then A is worded just like it was on your last test, except this one we only need 2 equations. So when we did quadratic, we needed 3, but when we do exponential, we only need 2 equations. And so we're going to take this, and we're going to plug the input and the output in to the function. Where are we going to put the input? A and B are going to be your variables. So A and B stay A and B. But you're going to put the input in for T. And you're going to put the output in for F of T. And so you would start off with 47 equals A times B to the second. And 2,602 equals A times B to the 20th. And then just like before, it is not okay for you to write f of 2 here. It actually needs to be 47, and it needs to be 2,602. Okay, that gets you a point on the AP exam. Super easy point to earn. You just leave A and B the variables, plug in your input and your output. All right, I feel like the next one is also a pretty easy one to earn. You have to put this data into your table. So, do you guys remember where to go? We're going to go to Stat, and then we're going to go to Edit. And I'm going to clear this out. This is probably like the next one or something. All right, so your input needs to be in list 1, and your output needs to be in list 2, and Briar needs you to do this. Once you get the data in, you're going to go to Stat, and then we're going to go to Calc, and then you're going to scroll down until you see exponential regression, which is going to be number 0. Alright, and then it's up to you. If you want to store your equation in list in Y1, you can. We're not using it on this particular one, so it doesn't really matter. All right, and then once you get that, the answer to B is just what you get for A. Make sure that you are accurate to 3 decimal places. Now, someone in my other class just likes to go to 4 decimal places, and that's fine. If you choose to round on this one, you cannot just make this 1.25. That is not right. If there was nothing after the 5, like if you weren't rounding, then it would be okay. But there's more things after it, so you have to go to 3. All right, any questions on that? Okay, let's look at example 3. So this is data that doesn't have context to it, so it's fine. We're going to do the same thing. But I want you to pay attention that this is a horizontal table. Does that mean that list 1 is going to be 3 and 21.54 and list 2 is going to be 8 and 3.62? No. You have to make list 1 be your input and list 2 be your output. That was an issue for someone on their last test. They tried to make the table match the horizontal table. Don't do that. That's crazy. So what we're going to do is go to our Stat Edit. List 1 is the X values, so 3 and 8. And list 2 is the G of X values. Oh, I got a little bit ahead of myself. We'll fix it though. All right, we still need to do part A. All right, so on part A, we're going to write the 2 equations. So G of X, which is going to be 21.54, is going to be equal to AB to the X that goes with that one, which is going to be 3. All right, you guys write the other equation for me, please. Did you just get here? All right, now we did already put that data in, so we can do calculate and then 0. There it is. So be careful on that B. B is either going to be 6.99 or 0.700. They're both absolutely perfect, but 0.7 will get you absolutely no points. Oh, I'm going to move this over so you get that right. You could also do 0.69999. That's okay. They're only going to look at 3. So the grader of your test just looks at 3 and then doesn't care what's after that. So if you're accurate to 3, you're good. Okay, then another thing, we're doing a lot of different things today. Another thing we're going to do is something that you did in Algebra 2, and it is writing equations for exponential growth and decay whenever something is growing or decaying by a percent. So like if you know that the value of your car is decreasing by 15% each year, or you know that the population is increasing by a certain amount each year, you can write your own equation. And so it's going to be something like f of x equals a. A is still the same thing, initial value. But the base is for increasing is going to be 1 plus r. And then for decreasing, the base is going to be 1 minus r. So on example 4, after 50 deer, 50 is important, are introduced into a large wooded area, the population of deer in the wooded area can be modeled by an exponential function, where t represents the number of years since the deer were first introduced to the wooded area. The population of deer increases by 13% each year. All right, so we're going to find the values of a and b and use these values to write an expression for d of t. So what is a going to be? 50. That's the initial amount of deer. All right, what about b? Yeah, so 13% is 0.13, and you just add that to 1, and that's your base. So d of t is 50 times 1.13 raised to the t. All right, and then the next question just wants you to use it to find the population of deer after 6 years. So they want you to find d of 6. So you guys try that on your own. To charge my Apple Pencil for a second. So it should be about 104 deer after 6 years. And out of everything we're learning today, I feel like part C is the most challenging. But I could be wrong. You might remember doing this in Algebra 2 and just be able to do it super quick. But what we're going to do is we're going to write an equivalent expression for D, where B indicates the increased factor in the deer each month. All right? And so what I do is I take what T originally is, which is years, and I'm going to figure out what that would be in terms of months. So if you know how many years have passed, what do you do to that value to figure out how many months has passed? Multiply by 12, so it would be 12t months. And so this is going to be the outside exponent. And so changing this to months, is that going to change your initial value? No. So it's still going to be the same. So it's still going to be d of t equals 50. All right. But instead of raising it to the t, we're actually raising it to the 12t. And then we have this 1.13. Now, is it okay just to do that? Is that going to change the value of the function? Definitely. We're going to have to counteract that somehow. And so how do you think you counteract it? We have to raise this to something that counteracts that, multiplying by 12. Dividing by 12. So we're going to raise it to the 1/12. Because the rule for exponents, that it might be a while since you've learned that, is when you have a power raised to power, you multiply that. When you multiply that, you just get the t again. So it hasn't changed anything. And so now we have a new b. When we take 1.13 and we raise it to the 1/12, it's actually 1.010. So this new b tells you the increase factor each month. So it looks like each month the amount of deer increased by 1%. So that's what they were looking for there. I guess, I don't know, something about my brain, that gets kind of confusing. Maybe you guys do it better. Okay, and then the last example is about the natural base E. E is Euler's number. Euler is back there, the red guy back there. And E is always the same thing. It is a non-repeating decimal, kind of like pi. So it's always about this value. It's never anything else. So E is not a variable. It is always about 2.718. And things in nature very commonly grow exponentially with E as the base. And so this example is talking about bacteria. Bacteria a lot of times will grow with E as the base. And so we know the equation for this bacteria growth. And the first problem wants us to find the average rate of change of B over the interval from 1 to 7. I really hope and pray that you guys know how to find the average rate of change of a function. We've done it since day one, pretty much. And so when you hear average rate of change or read average rate of change, I really hope you think, oh, this is just a slope formula where I'm going to subtract b of 7 minus b of 1 on the top of the fraction, and I'm going to subtract 7 minus 1 in the denominator. Now to me, I like to just go ahead, just to save myself time, and go to y equals and type in that function for b. Do you guys know how to get E? There's 2 E's on the calculator. 2 E's that stand for Euler's number on the calculator. Do you see them? They're blue. Yeah, second division gets you E. If you do second ln, it goes ahead and raises it to a power, which we have to on this one. Both of them will work though. Okay. So once you get that typed in, you'll have to use X instead of T. Then you can just go to the home screen, get your little fraction guy, and because it's in y1, we would just do y1 of 7 minus y1 of 1 over, you can do 7 minus 1, or you can just do 6, whichever you want to do. And there it is. Just be careful that you're accurate to 3 decimal places. What would the units be on this? Bacteria per hour. Very good. So we subtracted bacteria on the top and time on the bottom. All right. And now B is just a little, I think, a little easier than the one we just did. We already have this in our y1. So if we just want to find b of 15, we can just do y1 of 15. There it is. Now on this one, I would probably go ahead and write it to 3 decimal places. But I don't think you can have a partial bacteria. Then I would say, just like with the deer, about 1,708 bacteria. If this was a question on a free response question, there would be a range that you could give that would be acceptable. Okay. And then C and D are just practicing again, changing the unit of time. And so we want to find an equivalent expression for B, where for B, capital B of T, where lowercase b indicates the increased factor in bacteria each day. And so right now we have hours. So T hours translates to how many days? It's going to be a fraction of a day. 1/24th of a day. All right, so then it would be B of T. 17 doesn't change. All right, and this one is kind of weird because there's already a coefficient for T. So we just take the 1/24th and we multiply it by what's already there. Right, and then to counteract that, the E has to be raised to the 24th power. And we could do that. We could take E and raise it to 24th power, but it's a huge number. And your calculator will give you scientific notation, and it'll just look messy. So I'm going to leave it like this. Okay, and I want you guys to try and do D on your own. So we're going to do another equivalent expression where lowercase b represents the bacteria each minute. So we're going to go back to hours. And we're going to change the unit of time to minutes. This time we can't actually find the value of lowercase b. We would take E and raise it to the 1/60th. So you can do 1.016 or 1.017. All right, what questions do you guys